Download this code from codegive.com, link in the description below. Longitudinal Redundancy Check, LRC, a comprehensive tutorial. The Longitudinal Redundancy Check, LRC, also known as a checksum, is a simple error detection method used in data transmission and storage. It's designed to detect errors introduced during the process, like bit flips or alterations caused by noise or faulty hardware. While not as robust as more advanced methods like CRC, cyclic redundancy check, LRC is still valuable for its ease of implementation and low computational overhead, making it suitable for resource-constrained environments or applications where a moderate level of error detection is sufficient. How LRC works, the basic idea. The fundamental principle behind LRC is to generate a checksum value based on the data being transmitted or stored. This checksum is then appended to the data. At the receiving end, or during data retrieval, the checksum is recalculated using the same algorithm. If the recalculated checksum matches the transmitted, or stored, checksum, it's assumed the data is error-free, or at least, no errors were detected. If the checksums don't match, it indicates an error, and appropriate action can be taken, example requesting retransmission, logging the error, etc. The most common method for calculating the LRC involves performing a bitwise exclusive OR, XOR, operation on all the bytes, or blocks of data, being checked. Step-by-step explanation. Here's a detailed breakdown of the LRC process. 1. Data segmentation *. The data to be transmitted or stored is divided into equal-sized blocks, usually bytes. 2. Initialization *. A checksum accumulator is initialized to a specific value, often 0, 0x00 in hexadecimal. 3. Iterative XOR operation *. Each block of data is XORed with the current checksum accumulator. The result of the XOR operation becomes the new value of the checksum accumulator. This process is repeated for all data blocks. 4. Checksum calculation *. After all data blocks have been processed, the final value in the checksum accumulator represents the LRC checksum. 5. Transmission/storage *. The calculated LRC checksum is appended to the original data. This combined data, original data plus checksum, is then transmitted or stored. 6. Reception/retrieval *. At the receiving end, or when retrieving data, the data is separated from the appended checksum. 7. Checksum recalculation *. The receiver, or retrieval process, independently calculates the LRC checksum using the exact same algorithm and initialization value as the sender, or storage process. 8. Checksum comparison *. The recalculated checksum is compared to the received, or retrieved, checksum. 9. Error detection *. If the recalculated checksum matches the received/retrieved checksum, the data is considered valid, no errors detected. If the checksums do not match, an error is detected, and appropriate error handling measures are taken. Example. Let's illustrate with a simple example using ASCII characters represented as bytes. Assume we want to transmit the string ABC. 1. Data, ASCII representation. A equals 65, 0x41 in hexadecimal. B equals 66, 0x42 in hexadecimal. C equals 67, 0x43 in hexadecimal. 2. Initialization *. Checksum equals 0x00. 3. XOR operations *. Checksum equals checksum caret 0x41 equals checksum equals 0x00 caret 0x41 equals 0x41. Checksum equals checksum caret 0x42 equals checksum equals 0x41 caret 0x42 equals 0x03. Checksum equals checksum caret 0x43 equals checksum equals 0x03 caret 0x43 equals 0x40. For checksum asterisk the calculated LRC checksum is 0x40. 5 transmission asterisk the data transmitted would be ABC followed by the checksum byte 0x40. Receiver side asterisk 1 received data asterisk ABC and checksum 0x40. 2 recalculation asterisk the receiver performs the same XOR operations on ABC. Checksum equals 0x00 caret 0x41 equals 0x41. Checksum equals 0x41 caret 0x42 equals 0x03. Checksum equals 0x03 caret 0x43 equals 0x40. 3 comparison asterisk the recalculated checksum 0x40 is compared to the received checksum 0x40. 4 result asterisk the checksums match, so the data ABC is considered valid. Code example, Python. Here's a Python code example demonstrating LRC calculation and verification. Explanation of the Python code asterisk. Asterisk calculate underscore LRC, data, asterisk this function takes a byte array, bytes type in Python, as input and calculates the LRC checksum. It iterates through each byte, XORing it with the LRC accumulator. Finally, it returns the calculated LRC value, an integer. Asterisk verify underscore LRC, data, received underscore LRC, asterisk this function takes the data and the received LRC value as input. It recalculates the LRC using calculate underscore LRC, data, and compares the result with the received underscore LRC. It returns true if they match, indicating a valid checksum, and false otherwise. Asterisk example usage asterisk the code demonstrates how to use the functions. It calculates the LRC for ABC, prints the data and checksum, and then simulates the receiving side by verifying the checksum. It also shows how a single bit error in the data causes the checksum to fail. Code example, C. Explanation of the C code asterisk. Asterisk includes asterisk sto.h for standard input/output, printf, and stint.h for fixed width integer types, like uint8_t which is an unsigned 8-bit integer, perfect for representing bytes. Asterisk calculate underscore LRC, data, len, asterisk this function takes a pointer to an array of unsigned 8-bit integers, uint8_t asterisk data, representing the data and the length of the array, size_t len. It calculates the LRC checksum by XORing each byte with the LRC accumulator. Asterisk verify underscore LRC, data, len, received underscore LRC, asterisk this function takes the data, its length, and the received LRC value. It recalculates the LRC and compares it to the received LRC, returning 1, true, if they match and 0, false, otherwise. Asterisk main, asterisk the main function demonstrates how to use the calculate underscore LRC and verify underscore LRC functions. It initializes a byte array representing ABC, calculates the LRC, prints the data and checksum, and then simulates receiving the data and verifying the checksum. It also demonstrates the effect of a single bit error on the checksum verification. Limitations of LRC. While LRC is easy to implement, it has significant limitations. Asterisk sensitivity to even numbers of errors asterisk if 2 bits within a data block are flipped, both change from 0 to 1 or 1 to 0, the LRC will remain the same, and the error will go undetected. This is because XORing the same value twice cancels it out. In general, LRC struggles with an even number of bit errors, especially those that neatly cancel each other out. Asterisk error distribution asterisk LRC is better at detecting burst errors, where multiple consecutive bits are corrupted, than scattered single-bit errors, but its effectiveness depends on the burst length and location. Asterisk not suitable for critical data asterisk due to its limitations, LRC should not be used for applications where data integrity is paramount, such as financial transactions or critical control systems. More robust methods like CRC or hash functions with collision detection are preferred in those cases. Alternatives to LRC. Asterisk CRC, cyclic redundancy check CRC is a far more powerful error detection method. It uses polynomial division to generate a checksum, and it's much more effective at detecting various types of errors. CRC is widely used in network protocols, data storage, and file compression. Asterisk hash functions, example MD5, SHA-256 hash functions are designed for strong data integrity and are often used for cryptographic purposes, example verifying file integrity or password storage. They are typically more computationally expensive than LRC or CRC, but they provide a significantly higher level of error detection and protection against malicious tampering. However, hash functions are typically used for verifying entire files or large blocks of data, not usually for real-time error detection during transmission of small data packets. Asterisk parity checking asterisk a very basic error detection method that appends a single bit to a block of data. The parity bit indicates whether the number of ones in the data block is even parity, or odd parity. It can detect single-bit errors, but it is very limited. When to use LRC? Despite its limitations, LRC can be a suitable choice in the following scenarios. Asterisk resource-constrained environments asterisk where computational power and memory are limited, example embedded systems with simple microcontrollers. Asterisk low throughput communication asterisk when the data transmission rate is low, and the overhead of more complex error detection methods is not justified. Asterisk simple data integrity checks asterisk for applications where a moderate level of error detection is sufficient, and the cost of more robust methods outweighs the benefits. Asterisk legacy systems asterisk you might encounter LRC in older systems or protocols where it was originally implemented. Summary. LRC is a simple checksum method for error detection. It works by calculating a checksum based on XORing data blocks and appending it to the data. While easy to implement, it has limitations in detecting certain types of errors, particularly even numbers of bit errors. It's suitable for resource-constrained environments or applications where a moderate level of error detection is adequate. For higher data integrity requirements, consider using CRC or hash functions. Remember to always evaluate the specific needs of your application to determine the appropriate error detection method.